Today we're going to look at ways for approximating the area underneath the curve of a function. So in particular, if you have the graph of a function, something like this, and let's say we go between x is equal to a and x is equal to b, and suppose you want to compute the area underneath this graph. The idea is to use something called a Riemann sum. So this is Riemann sum. And the idea behind the Riemann sum is to break the interval from a to b down into a number of pieces called subintervals. Right? And then the idea is to approximate the area underneath the graph for each subinterval individually. So for this subinterval, we just have a smaller portion of the graph. We want to approximate the area underneath that smaller portion. Now, if we break down our subintervals into small enough pieces, the hope is that the function looks almost constant. Maybe there will be a slight variation, but we can treat it almost as constant. So the idea is we take any value of the height, for example, that y value right there, and then just use that as a constant value over the subinterval. So we get a rectangle that approximates the function for that particular subinterval. And then the area of this rectangle will approximate the area under the curve from this point to that point. And we do this for each of the subintervals. So maybe we use a point like that height right there. And for this one, maybe we use something like this. And for that one, like that. And for this one, something like this. Something like that. And then maybe something like that. So we basically have a number of rectangles, each approximating the function for their particular individual domains. So we pick some point on each subinterval and compute an output value of f of x, and f of x returns the height of the rectangle for some value of x on that interval. So we're going to formalize this notion in this video lecture. But this is the basic picture. So this is the big picture of what we're doing. So if you keep this in mind, and you can always let that basic picture guide you when you're writing down and figuring out your equations. Now the first step in computing a Riemann sum is to look at where the subintervals are. And to figure out the subintervals, we need to figure out how we place these little notches, right? We have a bunch of little notches that are placed between a and b, and those notches divide up the domain from a to b into a bunch of subintervals. So, and we have some notation that describe the placement of these notches. So let's just start by looking at the x-axis all by itself. So here we have x is equal to a, and over here we have x is equal to b. And we're going to place a number of little notches that basically define where the subintervals are. And so we need a nomenclature, a way of labeling these notches. So the standard approach is to say x0, x1, x2, x3, x4, and so forth. And then we'll end up with somewhere we'll have an ith. So I is basically a general index that just for an arbitrary notch, we call it x sub I. And then we let xi vary from 0 all the way up to n. And then let's say we end at x sub n. So let's say we have n subintervals. And then n would usually be given. So we divide our interval from a to b into n separate pieces. So this would be piece 1, piece 2, piece 3, piece 4, and so forth. Now notice that the right endpoint of piece 1, or subinterval number 1, is x1. And the right endpoint of piece 2 is x sub 2. And the right endpoint of part 3 is x sub 3, and so forth. So if we have n intervals, it makes sense that the right endpoint of the nth one will be called x sub n. So also what we note is that x sub 0 will always equal a, and x sub n will always equal b. Now the whole idea of this is, as we progress, is we're going to go back and, for a given function, compute this over and over again for different values of n. We'll make n larger and larger and see what happens. But for now, we just have one set of subintervals, so one division. So we divide it into n subintervals. So one thing we need to compute is delta x. So delta x is the width of each subinterval. So delta x is literally just that width. It's the change of x going from one notch to the next notch. And so if we have n of these notches between a and b, delta x should be b minus a divided by n. So it's a formula you should know. And it's better to understand the formula than to memorize it. I mean, it basically says, well, let's look at the whole length from a to b, so that's b minus a, and we're dividing it into n pieces, so it's b minus a over n. Right? So think about what the picture is, and you'll never get the formula wrong. So now we need a formula for x sub I. So x sub I is going to be basically where my ith notch is. And so, well, we can think about this before we write this down. Let's think about some special cases. Well, x sub 0 should equal a. X sub 1 should be a plus delta x, right? Because to get from x sub 0 to x sub 1, we need to add delta x. X sub 2 should equal a plus 2 times delta x, because getting from x sub 2 from x to x sub 2 from x sub 0, we have to add delta x twice. X sub 3 should equal a plus 3 delta x, and so forth. Now hopefully you're starting to see a pattern. X sub 1 is a plus 1 times delta x. X sub 2 is a plus 2 times delta x. X sub 3 is a plus 3 times delta x. So x sub I should be a plus I times delta x. If you remember where it comes from, you'll never forget the formula. Let's check it. If I is equal to 0, so we have x sub 0, we would get a, which means x sub 0 is equal to a. Now what if I is equal to n? X sub n is a plus n delta x. But that's equal to a plus n times delta x was b minus a divided by n. So the n's cancel, and we get a plus b minus a, which is just equal to b. So x sub n does check out. It works out to be b. So everything is lined up appropriately. So we have delta x is b minus a over n. X sub I is a plus I times delta x. And one final thing to note is the ith subinterval. So where does it run? So the ith subinterval runs from xi minus 1 to xi, right? And again, just look at the pattern. The first subinterval so x sub 1, or the first subinterval, runs from x sub 0 to x sub 1, right? Because the first one right here is sandwiched between x sub 0 and x sub 1. The second subinterval is between x sub 1 and x sub 2. So notice that first, it ends at x sub 1. Second ends at x sub 2. Third one goes from x sub 2 to x sub 3. So the ith one goes from x sub I minus 1 to x sub I. So if we say this is x I minus 1, this is our ith interval right here. It's between x sub I minus 1 and x sub I. Our nth one is between x sub n minus 1 to x sub n. So this tells us what the delta x is, where all the x sub i's are. So this tells me all my notches. And then this last equation reminds me that the ith subinterval is between x sub I minus 1 to x sub I. So all this is great. So now how do we do the Riemann sum? So we have x sub 0, x sub n. So x sub 0 is a, x sub n is b, and then we have x1, x2, x3, and then so forth. And then we have our function f of x. And we said that delta x was b minus a over n, x sub I is a plus I delta x, and our ith subinterval goes from x sub I minus 1 to xi. Now, for each of these subintervals, what we're going to do is approximate f of x at one of the points on the interval. So now I'm going to say let x sub I star be an element of the ith interval. So remember, this is our ith subinterval. This symbol here, it looks like an E, it's not an E, means contained in. So the interval is expressed by the square brackets. It's the interval from xi minus 1 to xi. So it's this interval right here. And then xi star is some element in this interval. In other words, this is the same as saying that xi minus 1 is less than or equal to xi star is less than or equal to x sub I. So basically, x sub I star is any x value in the, that's x sub I star, in the ith subinterval. So we're picking any single x value in the ith subinterval. Now later we'll talk about left-hand and right-hand Riemann sums. Left-hand Riemann sum says for xi star, always choose the left endpoint, which is x sub I minus 1. Right-hand Riemann says for xi star, always choose the right endpoint, which is x sub I. So those are two standard ways in which you might pick. And there's other ways. Technically, you can pick any point in the ith subinterval. It could even be random. You know, as long as you get some point here, you're approximating your function at some point in the interval, so basically this rectangle is going to approximate the area under the graph for that subinterval. Now the height, so the width is delta x, and the height of this rectangle is going to be f of x sub I star. So x sub I star is some point on the subinterval, and then if I just evaluate f of x sub I star, I get a height reading for that rectangle. So the width is delta x, and the height is f of x sub I star. So altogether, our Riemann sum, so the area, I'll call it delta a sub I. So this is the area of the ith slice. Call these things slices. Delta a sub I is going to be approximately f of x sub I star times delta x. So I'm approximating the area under the curve by taking the height at one point of the function f, multiplying it by a width to get an area for that rectangle. If I sum these over all of the subintervals, I get a rectangle for each subinterval. So I get a rectangle here, I get a rectangle here, I get a rectangle here. These are very quickly drawn rectangles like that. If I add up all the areas, I get an approximation for the area under the curve. And that's called a Riemann sum. So this is for a general Riemann sum. So again, so this is a Riemann sum with n subintervals. So first we let delta x equal b minus a over n. And then we say x sub I is equal to a plus I delta x. And then just a reminder, our ith subinterval is xi minus 1 to xi. And then let xi star be contained in xi minus 1 to xi. So these are the equations so far. So our Riemann sum with n subintervals is going to be the sum I equals 1 to n. So we want to sum up n of these because we have n rectangles, so we'll sum from 1 to n. F of x sub I star times delta x. So this is the height of the ith rectangle, and then this is the width. So when we multiply height by width, we get the area. So this is the area of the ith rectangle. And when we add them all together by doing a summation, we get an approximation for the area under the curve. So this formula is the formula for a Riemann sum with n subintervals. And these things are all computed based on the formulas that you see up here and from the function f of x.